We just found column space. Unfortunately, the audio didn't work properly. So I'm just going to go through, there are 2 pages of notes here, and we'll just work through them to get back where we were. All right. It was the most exciting thing I've ever recorded. But there you go. That's what happens. Tragedy. Right. So the search for column space. There's some music here, but budget issues. So we talked about how column space is the place where the b's live such that ax equals b has a solution. That is what this statement is here. And that it's a subspace of Rm, right? So A is m by n, right? M rows by n columns. It's a very confusing thing, but that's right. So the columns are m-dimensional. B is an m-dimensional column. We're trying to make B out of some linear combination of A's columns. That's where B lives. And if there's a solution, B has to live in column space, which is essentially all of the linear combinations of A's columns. We're trying to do something smart and find a clean description of that column space. And this is going to take a little while. We will have 3 different ways of finding column space, and they have different attributes, right? So some of them are more just for understanding. Some are, the one we'll get to at the end, I think it just takes a while to get there, but it's the best, right? So it's the best for understanding everything. But this is sort of an entry into it. So this is the first way to get there. So as I said, 3 ways to do it. There'll be 1 way to find null space. Just as happens sometimes, there's going to be this 1 way. We're just going to dictate that's the way to do it, and you can't go wrong. There's a little messing around with one or two of these other methods, really, and especially this first one. So what did we do? We, in the last piece, we reduced the matrix A, B, the augmented matrix, to the reduced row echelon form of A, and D was whatever came out. And we moved to this new thing where we said, well, let's just take B to be B1, B2, in principle down to Bm, and then just let those variables sit there, and we'll just move them around, right? Okay, so the plan now is, once we've done this row reduction, it's just row reduction that we've done before, except we go the step further where, as we did for inverses, we go a step further and we reduce completely. And I guess I can just show you this down here. Here's the Fezzik example, right? It's a 3 by 4. It's a nice big matrix of French origin. And the row reduction gave us this story. There were these 2 pivot columns, which look like they're exactly the first 2 columns of the identity matrix. That's always going to happen. And 2 free columns as well, right? And then there's this overall staircase structure. We don't care now if there are pivots missing, in a sense. This is the second pivot, actually, right? So there is a second pivot. Okay, looking through this, we've got some equation now that we would solve with back substitution. We'd look at the bottom equation. It's all zeros, and on the left-hand side, and so it's 0 times x1. That's what this is up here, 0 times x1 plus 0, right? Equals 0. So whatever's on the right-hand side must equal 0 if there's a solution. If it doesn't, if it's 7 or 13, there's no solution. And that's the sort of thing we ran up against earlier. All right? So that's what this blob up here is trying to say. Let me just draw that. Yeah. This piece here is saying for every row of zeros, the corresponding entry in D has to be 0. Good. So we're just going to enforce that, and that's what this is here. We've taken the right-hand side, B3 minus B2 minus 2B1, and we've just set it equal to 0. Now that's an equation of a plane if we make a little B1, B2, B3 space. That's an equation of a plane, right? That's true, but it's not, as I've said here, not super awesome. We want perhaps a better way of breaking this up. It's not the only way, but it's a better way, will be to do this kind of thing. So this, and for null space, it'll be very clear how we do this. So we can put these characters on the right-hand side. It's nice how it makes it green. Okay. B3 equals, we don't have to do this, but we're going to do it, and it's equals B2 plus 2B1, right, just from this equation. And so B3 is a dependent variable now in this little setup. These two are independent, so we're just going to say this is how we express independence. B1, B2 are elements of the real numbers. And then this, and it's written here, always do this, right? So B equals B1, B2, B3. Just line them up and then replace the dependent variables with what their expressions in terms of the independent ones. And the independent ones just stay there, right? We don't have expressions for them. They're free to do whatever they want. Again, much clearer in the null space story. So, and then we're just going to pull this vector apart. There's a B1 times 1 in the top entry. There are no B1s here, and then there's a 2B1 down here. So that's 102 times B1. Plus B2 appears here and here. So it's going to be 0, and it's a 1 and a 1. So if you multiply all this together, you'll reconstruct this piece we came from. So that's an important step, taking a vector that's got a mixture of things in it and then pulling them apart, and then having, you know, the clear independent variables sitting out in front of them with fixed vectors, right? So these are fixed vectors. Maybe that's a good thing to say. Right, so yes, we could just stop here, but it's much clearer to do this. Now what we can see is that column space, for a B to be in column space, it must be represented by this. We must be able to represent by some multiple of 102 and some multiple of 011. Which wasn't obvious if you go back to the original equation, original structure, right? Here are these 4 columns. It turns out that if you play around with those columns enough, they only amount to these 2 columns. Right, we could see the second column was just 2 times the first one, so we could get rid of that. It's not giving us anything new. And again, if you think of this as notes, right, here are 4 notes. We're trying to make a sound. Then really these notes aren't different, that different. They're actually really only 2 notes. We could say there are 2 notes, and then we could dial their volumes up and down. Think of it like that. So the formal way of writing this out will be column space of A equals something, and it equals a whole bunch of things, right? So many, many things. And I guess I had this piece here too, where B1 and B2 are elements of real numbers. You need to put that always. So this is, B is a vector in 3 dimensions, such that B is some multiple, it's exactly this expression, and then with curly brackets all around it. So that says what column space is, in this case, for Fezzik, our champion. All right, what's going on? This is it's a plane. It's a 2-dimensional subspace of R3. And so this is jumping a little bit. We're going to have to sort this out. Big deal is that the column space of A is a 2-dimensional subspace of, the big deal is actually this piece, is of 3 dimensions. And the rank of A will always be the dimension of column space. Let me say that again. The rank of A, which is R, little r, that's always going to be the dimension of column space. We go back to here. We had the number of pivot columns in the row reduced form, the reduced row echelon form of A. Right? For Fezzik, there were 2. That's its rank. And spectacularly, that will be the dimension of column space. So if it's a 2, it means it's a plane living in some space. And in this case, the bigger vector space is R3. So a bunch of notes. Because the column space doesn't fill up R3, AX equals B may or may not have solutions, right? So if B is in that plane, there are solutions. If it's not in the plane, right, sitting outside of it, then there's no solution. And again, later on, that's okay. We'll get our best solution. So we need to really understand this. There's nothing special about those 2 vectors in the end, right? So it's like saying, so we could have, so in this example, just doubled the first one, and then multiply the last one by -3. It's like taking I hat and J hat. We could double them. We could flip them. We could take a different basis. We're going to talk about bases next week. That would still give you the plane. So the plane is unique, if you like. Right, so the plane is unique, but the two vectors that we use to describe it are not. What we will see are there are better bases than others. It's just an unfortunate truth. There are beautiful bases, and there are bases that make no sense, really. All right. There's a harsh world, mathematics. Okay. So this is where we got our expression. This is our constraint on the b's, right? As long as this is true, then the b you have is in column space. But we could do it like this. We could, instead of putting b3 equals something, we could put b2 equals something. That's what this case is, right? So we've put b2, we've kept that on the left-hand side, multiplied by a negative number if you want to do it like that. b3 goes over the other way, and so on, right? So this could be the dependent variable, and then we'd build out from there. That would give us two different vectors, but again, all linear combinations would describe the same plane. Last point, and this starts to get a little, this is good thinking. I've written very nutritious. Okay, just concentrate on this one. There's an assignment problem that will cover this. This is our constraint, again, on the b's. If this is true, then b is in column space. If these are true for its entries, let's write this out as an ax equals b problem. We'll turn everything into an ax equals b problem if we can. Well, this is -2, -1, and 1, getting the order of them right. This is b1, b2, b3. So here's b1, b2, b3. That's an inner product, or dot product, equals 0, right? So 1 by 3, 3 by 1, 1 by 1. The 3's match up and you end up with a 1 by 1. And what is this? This is ax equals 0. Another way to see it, if you've done this sort of thing in calculus, this is these vectors are at right angles. Right? That's going to be a big deal to us, the whole right angle or orthogonal business. This is actually really a null space problem, which is really next for us. It's a null space problem. So we can find, it sounds a little crazy, but we can find the column space of A by solving a null space problem for these b's once we've got this constraint. I want you to think about that last part. It's a good thing to come back to. If you can understand that, then you'll have a lot of deep knowledge going on, but it's an extra piece here. All right, good. Next up is null space.